Hello, and welcome to the Blue Waters webinar. I'm Scott Lathrop with the Blue Waters Project at the National Center for Supercomputing Applications at the University of Illinois, and it's a pleasure to have you joining us today. I'm pleased to introduce Aaron Saxton, a data scientist here at NCSA working on the Blue Waters Project. And today he'll be talking about machine learning on Blue Waters using TensorFlow. With that, I'd like to turn it over to Aaron. Thank you.
Thank you, Scott. So, hello, thank you for that introduction. So I guess we'll dive right in and go over some of the topics that we'll go over today. So first of all, everything that we'll be talking about today, I want to make sure we establish with the backdrop of Blue Waters. TensorFlow and a lot of these data analytics systems, their natural spot that they grew up were more data center type environments, where Blue Waters is not that. It's one of these massively parallel supercomputers. So it has some extra features and abilities that I hope during my role here as the data scientist in the Blue Water Projects office, I can find ways of really taking advantage of that and crank out performance with packages that are traditionally not on supercomputers. So we'll be starting with a Blue Waters overview to establish that backdrop. However, it's not going to be a big part of the rest of the presentation. Then we'll go into some TensorFlow basics. This is just how you define variables and contexts and run sessions, and some of the basic architecture of TensorFlow. After that, I don't know how long it's been since you guys have had a math class, but I figured doing just a little bit of statistics review would be useful, even if you're like, oh, that's easy. Just seeing some of the basics hopefully will tickle your brain, and when we go into the harder stuff, it'll be a lower barrier to entry. Once we get through the statistics review, I'll talk about neural networks, just a simple version of them. Then convolutions, then we squeeze it all together in convolutional neural networks. After that, ImageNet. ImageNet is the data set that I'm going to be using as the example of this presentation. And we'll get into those details later. One thing I'm trying to provide the next topic, one thing I'm trying to provide our users is an example code base to launch off from. So that's where this Blue Waters TensorFlow process, that topic will come in. I've prepared some run scripts to extract data, compile it into a TensorFlow native format, and then kick off the basic distributed TensorFlow run. So we'll do some code tour through that, and then we'll go into distributed TensorFlow details about how it works out of the box. Basically how it works out of the box. One detail that I'm going to allude to is that the team here is trying very hard to optimize distributed TensorFlow to work well on Blue Waters. So we'll go through how it works out of the box, but keep in mind that hopefully in the near future, some of the details will change to really take advantage of, so that we can really take advantage of Blue Waters. And then lastly, whenever you run an algorithm, you hope to get some output that when you look at that output, it means something. Google and TensorFlow have created something called Tensor Board to look at graphs and checkpoints. And so I'll be taking you on a tour through one of the big examples we'll be working with today. Great. Okay, Blue Waters overview. This is at the top of the slide here. We have a panoramic view of literally what Blue Waters looks like. On the left are where all the compute blades are. In the middle is where a lot of the storage is. The middle and to the right, other people in the room might know this better than I do, is where most of the actual physical storage is. This sits here in Champaign, Illinois, over at the Petascale facility. So this computer's made up of a bunch of ADM interlogos processors, and a handful of GPUs. In particular, each one of those cabinets on the left has a blade that is displayed there in the center. These blades come in two different flavors, XE and XK. That's kind of the big point I'm trying to get at here. The XEs are basically only the ADM interlogos, where the XKs are a mixture of your NVIDIA Tesla GPUs and the interlogos. So if we go look at one of these blades, and furthermore, one super special secret sauce with our particular system is the thing connecting this is not your commodity, or not necessarily commodity, but not just InfiniBand or something like that. It's Craze Gemini interconnect, high bandwidth interconnect. So each one of these blades has 4 nodes. If it's an XE node, it has 4 nodes attached to them. If it's an XK node, it has 2 nodes attached to them. And here's a graphic representation of how that connectivity works. What's more, with all that computing power, we have access to huge amounts of storage. With Craze Synexions hosting the Scratch, Home, and Projects file system, Lustre file systems, in addition to our SpectraLogic tape storage. And what's more is we have a high-speed networking to other institutions around the world. So what I'm trying to say is we have huge amounts of resources here that we are really trying to get some of this machine learning to crank on. Okay, so hopefully that was mostly a review for everyone. TensorFlow basics. TensorFlow has a Python API. I'm about to go into some examples of that. Under the hood, it's C++ though. If Google had it their way, they would even get rid of the Python API. Google's vision for all of this is that we think more about the data and the training sets and the flow of data rather than literal instructions and operations. One of the punchlines near the end of this presentation is models that you run on systems at the scale of Blue Waters are big and cumbersome. No one person in this room is going to go design it and do something with it. You're going to recycle other people's work. So Google's vision is that we think about machine learning as more of flow of data and operations on that data rather than literal line-by-line code. For the time being, though, they've given us a Python API on top of the C++ inner workings. So that means underneath the hood, it's doing it's doing CUDA, and it's also doing multi-threading, whether that's p-threads or OpenMP. I haven't dug that deep to know exactly how they do their threading. The Python API is a mediator design pattern. What that means is that there's almost, my experience with mediator design patterns is that you almost develop kind of this meta programming language on top of whatever your host environment is. So the way you think about constructing your TensorFlow problems is you lay out your recipe for, okay, I want this as my input data. Then I want to do I want to pass it through some type of a synapse, and then I want to do a convolution on it. So you compile this recipe of operations to do on your data, and then you say, okay, TensorFlow, here it is. And then all the work that the TensorFlow team has done looks at that recipe and decides where to put that data, exactly which device to execute each of the instructions on. Python has a context manager feature, the with feature, and this is the way the TensorFlow API enters the mediator and exits it. So we'll go into a few more details about that in a little bit. So right, that's the workflow. Construct operations, assign name scopes or devices, and then tell TensorFlow to go do its business. So with that, I'm going to hop over and do a little, or so let's see, how does this, there we go. There are huge amounts of resources for all of this online. You know, we're a community that's very good at Google searching. I'm sure you've seen a lot of this. During this presentation, I'm going to try and point out the highlights of all this that will help you kind of short circuit your path to getting up and running on this. But just to get started, I want to do just a couple of basic things following this, where's my cursor? Following this this getting started guide. Let's see, how do I exit out of here? Okay, so we'll do a little bit of a demo. Let's see, and if anybody's having a problem seeing this, let me know. It happens that I'm on a login node right now on Blue Waters. If you get TensorFlow installed on your laptop or your desktop, you can do what I'm about to show you without any problems. Turns out I updated some packages on my local computer recently, and it screwed something up. So I had to mitigate that disaster this morning. I'm a big fan of stateful interactive IPython shell. So import TensorFlow as TF. Okay, so whenever you have a new environment, one of the first things you might want to do is construct variables. So in TensorFlow, you need to put a little bit of extra effort into it, saying, indeed, I want a TensorFlow style constant. Again, this is a mediator design pattern, so this line here is building an object A that later TensorFlow is going to go decide which device, which namespace, which item in your cluster do you want to go send this data. Let's see, there we go. Cool. So TF float 32. So nothing magical here. Just defining some variables. Again, the mediator design larger. Oops. Let's see. There. Hopefully won't have to. Much better. Okay. All right. So at this point, I've only constructed these objects. The takeaway is these things haven't really done anything yet. What's more is because they're Python objects, this addition here is a TensorFlow addition. This is a binary operator. It's doing its own special bit of magic to create this new variable called total. Again, this is indeed a tensor, as TensorFlow likes to manage it. To actually get a result out of this, we need to enter a session with TensorFlow or TensorFlow.session as sesh.run. Oops, run total. Let's go ahead and put a print on that. There's going to be a little bit of noise after this print statement because I'm on a login node without a GPU. It's, whoops. All right, live demo fail. Sesh. TFS sesh. Say that again? Thank you. There we go. Great. So the thing that this sesh run does is deliver that. All this is noise specific to Blue Waters. Basically, I'm running TensorFlow on a login node that doesn't have a GPU. Not the end of the world. Okay, great. So, so TensorFlow has gone and taken that A that I defined and the B and done some magic with it. What's more is behind the scenes, it's created what's called a graph for these operations. So if we want to see that graph, let's see, let's do tf.summary .file writer. Let's just dump it to the local directory. So to the writer, oops, I'm going to do a add, come on graph, there we go. TF get default graph. Okay, so again, because this is a mediator pattern, during this with statement up here, when we actually ran it, that's when it looked at all of the tensors I constructed in the lines above and decided how they all interconnected. And so it has already added all of that information to its global context. One detail that we'll see while we're perusing while we're doing a code tour is you can do lots of management with multiple graphs, multiple namespaces, and mix and match the way all these things interact with each other. So bam, I wrote it. One detail, let's see, simple graph. Okay, so one detail, that file technically is sitting over in the login node. I have indeed secure copied it to my local computer. If you were doing this locally, that would have been a non-issue. So here, let's make this bigger. TensorBoard. Go ahead and get TensorBoard installed. I'm a big fan of pip. I use pip to manage all my packages. It installed super easily for me. So if you have your Python environment set up nice, pip install TensorBoard. And in your environment, you will get, or in your path, you will get a new command called TensorBoard. So you say it TensorBoard -- log directory. It turns out I'm in the directory where the output. Oh, let me point that out. Oops. When I did writer add graph, this is the file it created. One of those. That's the file that I've moved over here and is currently sitting in my directory. Okay, so when I do log directory / that's the thing it's looking for. All right, now, oh my, okay, that's fine. So TensorBoard behaves a lot like Jupyter. It's setting up a little web server on your local machine. And in fact, it's telling you, hey, go look at this URL if you want to see the output of TensorBoard. It turns out, I'm not sure if this part of the URL is going to work very well, but this socket here is what's super important. Localhost 6006. All right, that's the point. Magically, you did a handful of operations, with TensorFlow, defining some constants in operation. You handed it off to a session to actually perform the operation. It went and figured out how everything is related and where to run it. And TensorBoard is the thing that helps you see literally what it's doing. So the message I tried to give you guys earlier, if Google has it their way, this is the way we'll always be dealing with machine learning. Just big graphical representations of data flowing. It's not quite there yet. I want to venture to say that this became public, I think, last year. So it's still being developed and moving forward. What I'm finding is this is a good tool for debugging. It's a good tool to, when we're dealing with these massive graphs for training models and whatnot, it's a good way to look at it and say, there's probably something wrong. So, okay. So TensorFlow and TensorBoard. There's some introduction to it. As I was saying before, there's huge amounts of resources to get into the nitty-gritty detail about this. I encourage you, if you're a first-time user, or even if you're not a first-time user, you've kind of been hacking your way through, perusing this and looking at some of these examples sharpens your ability to just pop something up and do some experiments. Okay. And now I want to go back to you. Demo. Okay, statistics review. So reviewing some of the math that you probably knew super well at one point, or if you are in the midst of it right now, you know it really well. Regressions. I'm a trained mathematician, so I feel a little bit dirty about saying this, but neural networks are nothing more than glorified regressions. That's not entirely true, but for argument's sake, let's move forward with that. So we'll start with the simplest regression, a linear regression. With a linear regression, the problem is you have a general equation for a line, y equals mx plus b. Your m and your b are parameters that you can choose in all sorts of weird ways to represent this red line. You also have a data set of inputs. Typically, these inputs are dependent variables and outputs. Independent variables and outputs, dependent variables. So typically, your x is something easy to measure, is something easy to dream up. Time, a person's age, something like that, where y is something usually a little bit harder to measure. How many years of school do you have, or what's your chance of cancer? Something a little bit harder to measure. And so for a simple 2D problem, your data is usually scattered all over the place. If you were able to isolate 100% causal, I don't want to say causal, but 100% relationship between your input and output, your data would be nice. Where's my pointer? There it is. Your data would be nice and straight here, but chances are whatever experiment you're doing, there's noise in it, and it's somehow affecting the output. So the goal is to find a particular M and a particular B that best fits, that warm fuzzy notion of best fits this cloud of data. One of the first ways that we learn how to do this is with least squares. So with least squares, the starting point for least squares is computing the error between some yet to be found mx plus b and your actual output data. So for each one of your data points, your output data y sub I minus this mx plus b model, evaluated at the corresponding input. We square it, or we take the difference, that's your error, we square it, and we sum it. So this is what we're going to use to represent our error. Whoops, I changed symbols because I changed text. So our goal here is to minimize R with respect to M and B. For those of you who remember your Calc 1, we have, where's my pointer? We have this big sum, but it's only a quadratic. Yeah, it might be big and long, but it's not that complicated. So if we want to minimize something, take some derivatives. Take your partial with respect to M, take your partial with respect to B, set them equal to 0, and simultaneously solve this system of equations to find your M and B. In a nutshell, that is least squares. Mini classes will use this example to teach matrix algebra and solving systems of equations because it all just falls out so nicely like this. What's more is because you're solving this linear system, you can kind of see why machine learning does boil down to tensor operations. That's a detail I'm not going to go into today, but this kind of hints at that's all this machine learning really is just linear operations after linear operations. Okay, so you don't have to do a regression with just a line. You can do regressions with all sorts of crazy functions. Your linear system probably isn't going to be linear anymore. So there are additional techniques. I opted not to talk about it too much today, but gradient descent and stochastic gradient descent is the typical way that you would go about optimizing your parameters to get a good fit. So just to kind of build up in our brains that, okay, well, you can do a quadratic fit or quadratic regression. You can do a polynomial where your unknown parameters are A, B, and C. You can do a polynomial regression where whatever degree your polynomial is, that's how many parameters you'll have to solve for. Exponential regressions, logistic regressions. These are all forms of functions that we can parameterize and fit to some cloud of data. So from statistics, the point of all this, after optimal parameters are found, the point of all this is to use that as a model for inference. Again, I emphasize that often your x sub i's are something easy to measure, your y sub i's are something hard to measure. So you want a model that you can pick up and carry with you later so that when you get new additional x sub i's, you can infer what that output should be. So have x compute y. That's the whole point of this. All right, so before I get into some of the nitty-gritties about what okay, so with that said, regressions, neural networks are nothing more than fancy regressions. Before we get into some of those nitty-gritty details, I want to introduce some of the basic building blocks of neural networks. Activation functions. So I have 3 examples of activation functions. Logistic. So this is just something that whenever you put in, whenever you give an input that's very negative, it's very small, and it smoothly grows. That whenever you put in something that's very positive, you get it's asymptotic at 1. You can also use arctan. The latest craze is this thing called a rectified linear unit, or an RELU. It turns out that this we have this nice little 0 when something's very negative, and growth as you get larger. Yeah, that kind of represents this linear growth in the logistic and the arctan. Recent papers suggest that if we substitute our activation functions for this oversimplified model, doing the computation of evaluating a line, an identity line at that, compared to having to do maybe some power series or however the hardware level would evaluate a logistic function or an arctan. The computational performance of RELU is much better than logistic and arctan, with only small amounts lost to training speeds and whatnot. So most modern models, most modern neural networks use RELUs, or rectifiers. The other ingredient to neural networks is something called a softmax. This is a way of normalizing data on the output layer, which I'll get to in a second. So a softmax, PowerPoint didn't format the subscripts very well, but basically the kth softmax, if you pass in a big long vector, it basically exponentiates, raises to e all the pieces, and sums them all up, and then in the for the denominator and the numerator, it just takes the particular component you want. The important detail about this is that if you sum up all these softmaxes, a little bit of college algebra, we'll see that if you sum up all the softmaxes, they sum to 1. And that's the point, is it's a way of normalizing your outputs. Okay, so basic neural network. So we have a vector for inputs. We have 3 inputs. We have a hidden layer. And we have, in this particular diagram, 2 outputs. Great. So here, our hidden layer is what we're computing the activation function for. So our hidden layer, we take our vector of inputs. Sorry, there we go. We take our layer of inputs, our x. We multiply it by some constant. This guy here, keep in mind that this is a vector. This is basically a dot product between two vectors. So this, in this graphical representation, this is a 3 vector and this is a 3 vector, plus some bias. All right, so we take our inputs, we multiply it by a weight, and we add the bias to it, and that represents for the mth synapse in the hidden layer, that represents what value that should be if you give it a particular input. From that input, we map it to one of 2 outputs. So all these m's together represent a vector. This beta here times our vector. So this is another weight. So we give it an input. It does this computation. It feeds it into the activation function. It spits out a value. We take that value. We multiply by additional weight, add it to a bias, and this would be the raw output. It turns out most modern neural networks apply the softmax to normalize the output. So, for example, let's say we have an input of 0, 0, 1/3, and some arbitrary weight. All right, that weight would get the first component multiplied by a 0, second component multiplied by a 0, and third component multiplied by a 1/3. So the mth hidden layer here would get the result of multiplying 1/3 times whatever the mth weight is fed through your activation function, and that would cause this particular synapse to light up, to either be high or low. Okay, so the value of z at the mth position is either high or low, depending on how you choose your weight here. Furthermore, we go ahead and multiply that by an additional weight, and that's what causes our output. So that's our input of x and output of y through this recipe. So the goal here, so all these betas and alphas, weights to be optimized, just like in that least square problem. So the goal is finding these weights. The magical piece of calculus that does this is an operation called backpropagation. I'll go into a little bit of this detail here in a second. I feel like I'm talking way too much about this, so I'm probably going to gloss over this a little bit quickly. Backpropagation is nothing more than fancy chain rule. So take partial derivatives and work your way back through your network. So if we go back up here, right, this function, or this linear function here is composed in your activation function. That activation function is composed in this linear combination. So taking a derivative of your f basically will cause a big long sum big long product from your chain rule. What's more is I wanted to take this opportunity to point out one of the texts that is my go-to for all these nitty-gritty details. So in all of that, if some of it was a little bit unclear, I encourage you to go look at this Elements of Statistical Learning, second edition by these authors. So this is the text I'm going to go to real quick to point out some details about backpropagation. All right, so let's see, we're on page 396. So here's the cover. This is my go-to. This is a little bit older, but even as everything's gotten fancier and the community has decided what better practices are, most everything the community is talking about, all its ingredients to the neural networks and whatnot are buried in here. 390. So backpropagation. Again, to optimize your neural network, you need some kind of error function. The example we used earlier was least squared. You take your output, you difference it. You take your measured output, you difference it from what your expected model output is. So this function here is a parameterized collection of functions of all the different weights. That's what this theta is this big long vector of all the different alphas and betas. Another way of measuring errors through cross entropy, it's just another way of calculating error or loss. Okay, so literally, it is taking partial derivatives of your error function. It turns out that this, after you do that calculation, this is what you get. Things I want to point out is that the values of your hidden layer are buried in this backpropagation calculation. Or in other words, the process by training these models means you need to take your input data, feed it, or let me start a little bit. You need to choose an arbitrary set of weights to initialize your model, feed your input data through your model with those weights, and that gives you some values for your hidden layer. Then the backpropagation tells you how to compute the weights as you move backwards through that model at some learning rate. Or in other words, backpropagation is start with passing your data through your model, get the values of all those z's, and then moving it back forward to re-estimate all your weights. And this is an iterative process. You can do it ad infinitum if you want to, or usually you do it up until you feel good about your result. And we'll get into details about that. Okay. Phew. Okay, so that learning rate from those formulas, that gamma sub I, that is your gradient descent. Those equations were telling you how to move through the parameter space to try and find the optimal collection of betas to fit your neural network. Okay, phew. All right, so that's kind of the one of the second big math thing I want to go through. The last big math thing I want to go through is convolutions. I won't belabor this too much. Convolutions are exactly what you learn about in maybe a graduate level differential equations course or an image processing course. A convolution is a way of mixing two functions. It turns out that you can represent, if you want to transform a function into something else, it turns out there's you can represent a lot of those convolutions by simply choosing an additional function and convolving them together. Convolution is an integral operator with a kernel. We often call the G a kernel. And here's your graphical representation of what's going on. As you vary x, you're translating your kernel G across f, producting all their values, and then adding them all up. So the red window here is your kernel, is your G. The blue window here is your sort of your input function. And this black line here is the result of the convolution. When you do a square window like this, it turns out that this is a rolling average. So if you choose G to just be this block square, it turns out that this is just a rolling average on F. So if you chose G as this square kernel and convolve it with F, that's another way of doing a rolling average. All right. So this talk, we're going to talk about convolutional neural networks. So we did some statistics review, we did some neural network review. Now let's figure out how to start piecing all this together with image kernels and convolutions on images. So is this big enough for everyone? Good. Okay, so here's sort of a simplified version of a picture. A little thumbnail, super pixelated, grayscale. Color images have multiple channels, may even have alpha channels and additional properties. But all of it boils down to this little pixel here has a numerical representation, 255. This little pixel here has numerical representation. That's hard for me to see. That's probably 50. So low value means black, high value means white, and then all the grayscales in between. Okay, so if we want to perform a convolution on this image, we create a stencil. I don't know if this article calls it a stencil. We create a stencil, basically an array. I shy away from calling this a literal matrix because there'll be no matrix multiplication. It's a window. This happens to be a 3x3 window. And the operation of convolution is analogous to the one-dimensional case that we showed in the previous slide. We pick a pixel. Let's see. Okay, we pick a pixel that we want to populate. On the input, that 3x3 stencil covers several pixels. We take our stencil and pointwise multiply the values of your stencil times the value of your image. So I can't move my cursor, but in the middle there you see the arithmetic being worked out for you. So it looks like there's a pixel that has value 206 times the 0 value in the stencil, plus a pixel with another value of 206 times the stencil value of -1. And so forth, and add it all up. where's my cursor? There it is. And that is the result of that pixel there. So people like to point out that on the edges, you have an edge here that's a little bit weird. You have to modify your process a little bit, but you move one pixel in, and it's exactly what we described. Question mark, and back here. All right, now I'm not an image processing expert. Back when I was in middle school a long time ago, I used to have a painting, one of these drawing programs that had a feature called filters. And you could play around with these stencils. As I got older and learned about more details, these are called kernels. And you could play around with these stencils. Maybe the image processing community kind of has classified these and knows, which stencils do what nice things. I personally cannot look at the stencil and be like, oh, that's clearly a sharpen. Or that's clearly a blur. But the point is, so let's go down here to a more robust image. And let's start playing around with some of these values. Okay, let's Sobel, bottom Sobel. If I'm pronouncing that wrong, custom, I guess, let's do. So if I start playing around with these things, all right, well, that's not terribly surprising. I make it closer to 0 and it wipes out most of the image. I make it bigger, and it starts to reveal some of the image. All right, it's still a little weird. It looks like it's adding some texture features in there. But me as a non-expert, and even the image processing community, I don't know if they've developed a taxonomy of what all these operations are. Yeah. So kind of like a rolling average, but a Gaussian rolling average. Neat. Yeah.
So blur is doing a Gaussian operation as well as, for example, the other thing. I'm not sure if there might be an edge.
Yeah, there was a. Isn't a Sobel an edge?
Yeah. Some of those things use the Laplacian of Gaussian. So those are the operations internally. They
Right.
basically take out the values of it and then create a filter.
Right, and average it up. So the Gaussians, that kind of makes sense why it's a blur. I don't know why this would necessarily be an edge detection, though. Yeah. Right, and there are experts that know more about this than I do. But the point I'm trying to get across, though, is there's a wide variety of things you can do with this that who knows what they're doing. There's a wide variety of these stencils and these values that who knows what they're doing. And the point of one of the big themes of a convolutional neural network is that these stencils are trainable parameters. They're unknowns, the same way the weights were. Cool. Okay, so that was the message I wanted to get through by popping over to this example. All right. Whenever someone comes by my office and asks me about convolutional neural networks, this is usually the first website I go to. It's a good resource. I handed these slides off to the organizers, so hopefully these will be available to you shortly. I've made some edits, though, so I need to get them a better version of this. All right, I've spent 49 minutes going over basics. Convolutional neural networks. There's huge amounts of literature out there. It's a very active field. Roughly 2012 is when these things took off. The resource that I found that allowed me to start dipping my toes into this world is this link here. It's basically a blog entry of someone who went and did a literature review. Whenever I'm at conferences and reading other papers, it's pretty good. The things he references are very foundational. In particular, AlexNet. AlexNet was one of the first convolutional neural networks that had some success. Up until this point, neural networks back in the 90s, neural networks they had some success using them for handwriting recognition, detecting characters from handwriting, and voice recognition. If you guys remember the Apple Newton, that was one of the best things on the market. It was doing some of these. But for those of you who were paying attention to this type of stuff back then, this field got kind of quiet for a while. I'm sure there were successes, and if you threw bigger computing resources at it and better data sets, you were making some progress. But AlexNet in 2012 was one of the big breakthroughs that said, okay, with a reasonable amount of data, I can do image feature detection. That is, I can pass an image into the inputs of this neural net. So images have huge amounts of variables. Have huge amounts of variables. The example we'll go through later, I think we parse everything down to a 299 by 299 image, 3 channels on top of that for RGB. So whatever that multiplies out to be, that's its input. One of the big points of the convolutions is to try and reduce some of that dimensionality. Well, it's supposed to do 2 different things. One other point that I wanted to make, and that one of the gentlemen here kind of made, is that these kernels, like with the blur, there's a kind of a high value in the middle of the stencil, low values all around. What this stencil is doing is it's combining spatial information. So the thing on the left, you have a 3 by 3 swath of adjacent, of spatially adjacent, not data adjacent, spatially adjacent data. And it's getting mapped onto a single pixel on the right. So these stencils, in some sense, are encoding spatial information for us, which is part of the breakthrough. So AlexNet, AlexNet was, while there were previous attempts at doing this, was certainly does this. So it applies convolutional layers to max pooling layers. Max pooling is sort of a dumb stencil. It just says take all these things together and add it up. And passes it forward to somewhere in this diagram. This one might not have it. I'll show with one of the other neural network graphs. I'll point it out to a traditional neural network all-to-all connect. That all-to-all is like that. The example that the simple example that I showed you of the neural network earlier. It's an input layer, a hidden layer, and an output layer. One detail that if you dig into these papers is, I'm not going to sort through it right now. One detail is a breakthrough with all of this is how they manage the data flow. I'm forgetting the name of the particular box, but one of the breakthroughs was after you do a convolution, you pass through the original image and do another combination of the two. So it turned out that convolutions by themselves were a little too strong to do classification on, but convolutions, while still keeping the original, while passing through some of the original image data, wound up being one of the breakthroughs that allowed these networks to do inference or to do inference on image type data. Okay, so there were other breakthroughs, and there are details on this. Here we go. So one of the reasons I belabored that image kernel. Here's a display of what some of those transformations look like. I would have never guessed that Here, let me make this bigger. I'm sure either everybody's asleep or somebody's complaining about how small this is. So the input layer of these particular images, applying some trained convolutions to them, and for some reason this pattern here helps classify some feature from the previous layer. These features here magically classify some features that were back here. So after you train these networks, some of these layers are going to be huge collections of these convolution stencils that who knows what exactly they're going to look like. As far as I know, the conventional wisdom is to try not to make sense of it. Basically, let the black box be a black box. The message there, though, is that means you have to be a good steward of your data. Your validation, your training data and validation data and testing data. Don't cherry pick it. Don't overlap it. Don't think you're going to do something clever with it. Pick it blindly and be true to it. Later, I'll try and get into some of those details. Oops. Cool. Let's see. Let's move back out here. There we go. Okay, so VGGNet, this is another popular one people like to do benchmarking and research with. So AlexNet was kind of the first. There have been iterations on it. VGGNet, GoogleNet. GoogleNet one of these image recognition competitions a few years ago. I think back in 2015. GoogleNet is ginormous. There's a little GIF down here, pointing out how ridiculously big this thing is. The reason I'm pointing this out to you, yes, go try and build your own homegrown models. Great. The direction this industry is going is, people are doing research on these models, publishing papers about how good they are on certain tasks. If you have a task similar to what some other group has done, use their model, use it to get started with, and then then your particular research project has its own unique data domain, and try and apply it to it and see what happens. I'm not saying that someday we might not have a taxonomy of how these work, and you could start from first principles yourself. But at the moment, the state of the industry is these things are huge. They're black boxes. Teams are toiling away at just figuring out ways to improve this. Once those teams do, your particular research, take what they've learned and go. So this big, if I remember correctly, this GIF here represents one of these layers in GoogleNet. So it's ridiculously big. We will get to it today. The example that I'm going to point out, the untrained model is about 700 megabytes. when it gets saved. So that was just naively taking somebody else's work, loading it in, and training it on a few samples. So these things are getting big. It's kind of on that cusp. You can probably do it on your desktop commodity hardware, but it's right on that cusp, and to do it on a larger type system, for instance, a system like Blue Waters. Okay. Oh, GoogleNet is Inception. So if you hear about Inception, I think the nomenclature, they start to talk about these nodes as being Inception nodes, and so the full thing together is a GoogleNet. Okay. So 5x5 convolutions, 3x3 convolutions, silly 1x1 convolutions, but they add degrees of freedom. And furthermore, they get recombined They get done in parallel and then recombined. You need to go deeper. ResNet. ResNet, I think it's been a few months since I've really dug into the literature. ResNet had some of the best performance in terms of putting images in and then successfully classifying their outputs. And ResNet was a Microsoft research project. So this one's popping up in research a lot. Oh, right. This is what I was telling about passing the image forward. I thought, it's been a couple months since I read the AlexNet paper. I thought they pointed something like this out. I might be getting it confused. Cool. All right, so there's huge amounts of literature out there about convolutional neural networks. So far in today's presentation, we've gone through the basic ingredients. I haven't dug too deeply in them. I encourage you to go read up on it and learn more about it. There are lots of super interesting details buried inside there. This this blog here is a good place to start. It's 2018, so this is about 3 years old. Cool. Highlights: AlexNet, VGGNet, GoogleNet, Inception, and Microsoft ResNet. Whew. All right, I'm going to take a drink. Do we have any questions, any comments so far?
If you have questions, you can post them on the YouTube live chat, but not currently.
Cool. Just a little bit about my background. I earned my PhD in mathematics, studying differential equations and operator theory. So this was a very nice extension. That's why I enjoy when I see convolutions and that kind of thing pop up. You can represent lots of differential operators with convolutions. So this was a nice mixture. Okay. So we've talked a lot about the model so far. How do we build these these statistical models and whatnot? Now we're going to talk about the data. Great. So this talk is about doing feature detection on images. Well, that means we need a data set that has features or annotations, as ImageNet likes to call them. ImageNet is a project that was started by I'm going to be embarrassed here. Fifi Lee from Stanford. Yeah, I think she's given some TED Talks. Very popular figure. She started this project where she said, "Okay, if I have a whole bunch of images, how do I? What's in them? What is this image of?" So her and a team got together and literally started annotating. I'm telling this story a little bit because a lot of projects that I've talked to other researchers around here about, that's part of their problem, is they have this input data set that they want to do amazing things with, and there might be some unsupervised learning thing going on in there. But honestly, the quote-unquote low-hanging fruit that they want to do is they need annotations on that data. Does this piece of data represent a good log message or a bad log message, for instance? Does this image represent a cloud or an ice cap? Those are some of the things going around. So so the ImageNet started, I think, roughly back in 2010. It might have had its infancy a little bit before that, but 2010 was the first time I started that I can find references to it. About this group that got together and collects images across the internet. These images are not ImageNets. They are They are whoever they got it from. Collecting these images, and they sat down and they put bounding boxes in them, or they put they say that this image represents this kind of scene or this kind of thing. So this example, let's see, where's my cursor? There it is. This example here represents that a little bit. We have some image of a scene. Maybe you're restoring an old 100-year-old home, and when you look at this, you see a wood floor. Well, they didn't annotate it. They didn't annotate a wood floor. What they did do, though, is annotate it as a dog, a child, a chair. Oh, there happen to be 2 chairs in this image. One's a little bit hard to see. I don't know if that's going to help or hurt the training. So humans have gone through all these images and annotated them. There are, 14 million images currently in their database. So with, 21, I should have put a comma in there, with almost 22,000 sin sets. Okay, so a sin set, a single sin set is a code to represent a label. Off the top of my head, a dog has a sin set. Chair has its own unique sin set. So they have gone through this many images and applied this many labels to them. How many bounding boxes, off the top of my head? I think on their website they might have that stat. The local data set, I counted that once. I can't remember exactly what it is. ImageNet runs this competition called the Large Scale Visual Recognition Challenge. So every year, of all their ImageNet data set, they collect a subset of it, and they call this the training set, and they give it out to the community, and they say, go train a neural network to take this image as an input, and as an output, return a bounding box. A bounding box is 2 ordered pairs representing the corners. Whoops, they probably, depending on where positives are 2 ordered pairs. So a bounding box is 4 integers. 2 of them representing this corner and 2 of them representing this corner. So this challenge says, go put a image into your model and output a value for the bounding boxes. What's more is a value for the corners of the bounding box and a label of what that bounding box represents. So a good convolutional neural network, if you give it this image, it'll spit out a sin set of dog with 4 numbers representing this point here and that point there. Okay, so let's see. I can see good. Let's play around a little bit. I find people just say, "Oh, there's this data out there," and they don't play with it any. So the ImageNet project has their website. This website, its performance sometimes is lightning fast and sometimes isn't. I'm pretty sure this is hosted on the same server that hosts the entire database. So if workshops are going on, or if somebody's trying to do some project, this thing speeds up and lags with it. And that'll become important later. Yeah. Okay, so enter some term. Seashore. Sorry, guys. That was embarrassing. One word. So it went and searched through its database, and it found labels that match seashore. Since that's seashore, seashore also is kind of synonymous with coast, sea-coast, sea-coast. But there's other synsets called, let me make this bigger. There we go. Called seashore mallow. I guess this is a flower. I didn't know that before now. let's, one I liked looking at yesterday. Okay, so, but one thing about looking at these images, again, I look at this image here. Okay, yeah, that's a seashore, but I also see a lot of clouds. Let's say I was an atmospheric scientist and I saw this and I thought, oh, those are such and such. It's really neat coming over. I think that's a mountain in the background. Oh yeah, by the way, there's a seashore. What I'm trying to say is that this data set is high quality. They've put a lot of work into doing this, but you know, your data, your labels on your data aren't necessarily definitive either. Is this image a typical representation of a seashore or of a skyline? Oh, hey, let's. Is that 2 words? 2 words. I'm a mathematician. Sorry, guys. Did I do that right? Not available. Oh, not available yet. Okay. Well, darn. I went off the reservation and didn't do anything. So ImageNet has this tool. So it dug me into all the other images that it considered similar. And click in here. Presumably, this is how they're allowing their team to go through and annotate these. Is this a typical seashore? Sort of. I might call it a more typical beach. I'm not going to click it. I don't want to screw up their data. Okay, so the point is that even though this is a very high quality data set, there's still a lot of room to add your own semantics onto this. Those are details that I personally am interested. Oh, wait, what was that one? It had a typical 2. So for some reason, 2 people thought that this is a typical seashore. Cool. All right, so while I'm here, let's go back to here, 0. Oh, let's, maybe we can come back here. Okay. All right, so what I was saying a second ago is there's a lot of room to wiggle around about semantics. ImageNet has basically said, okay, that's an interesting problem, good for you guys. We're gonna let this Princeton group manage the way the semantics and the relationships between things work. So that's where the SYN set comes from the Princeton University project WordNet. Just a real quick, let's dig through here. Seashell. So in the WordNet database, there's a SYN set called Seashell. It's a noun, it's a thing. Oh, I looked up what that meant the other day, I forgot. So this is WordNet's relationship to other SYN sets. Let's see, hardly large. So it has a definition of it. Oh, a shell. Covering, natural covering. Seashells indeed cover an organism inside. A shell, a whole, a unit? I don't know why that would be a relationship. How big is that part compared to the whole? Oh, a natural object. So these are all nested versions of here. So the point is, WordNet has this huge semantic graph of relationships between all these SYN sets. Maybe we can, when looking at a scene, maybe we can use some of those semantics to try and decide, is this scene of a wood floor or of a child playing with a dog? So that's some of the data, some of the input data for our problem. The good news is ImageNet, oh good, there's a link on the other page. Okay, Blue Waters has a copy of ImageNet. ImageNet is very useful for benchmarking. That's some of the first projects I've been working on, is benchmarking TensorFlow on Blue Waters. We're getting good performance, relatively speaking. And it took me a long time to get this ImageNet. data onto Blue Waters, if anybody has tried to do this. Like I was saying earlier, all this data is hosted in this ImageNet project's server. I don't know exactly what piece of hardware this is hosted on. While I was trying to download it, it took me about 3 weeks. Actual downloading time was probably about a week. There was a failure in the middle of it. Looking at some of the behavior, I think they updated something and I got hosed in the middle of one of my downloads. My point is, if you want to do research with neural networks and you need some data set just to get off the ground, ImageNet is a very good place to start. And we have a copy of it. Like I was saying earlier, ImageNet does not own any of these images. They're scraping the internet and then feeding it to humans to annotate it. The literal ImageNet API is a RESTful API. So once you get your models trained, if you just want it kind of crawling whatever ImageNet is doing, you can set up a RESTful API to grab whatever the newest, latest, greatest things are. And that API delivers URLs to the original image. If the original host nukes that image, then the URL will be invalid. But the point is, there's a little bit of terms of access. These terms of access are very open. Researchers in education, they don't care, don't make money from it. So if with your Blue Waters allocation, you go train this awesome model and you publish something on it, don't go and try and start Uber's competitor with it. What I'm trying to say is, if you want access to it, I need a very light amount of assurance that you at least know what the terms are. On the right-hand side is an example. It's very short. Basically says education and researcher don't make money. And that researchers are allowed to share it with researchers as long as the people they're sharing it with understand that this is what's going on. For me to give you access to this, I will want you to go to ImageNet, go create a user. Whoops. Max is going to yell at me. Since I've already accepted this, oh, maybe not. It didn't show it, or you guys didn't see it. Since I've already accepted this, I don't know how to go through the same pathway. Basically, go accept this. Either print this off. Can you download it? At one point, I thought there's a download button. Either take a screenshot of this, print it to a PDF, do whatever you have to so that I see your name here and the rest of this agreement, and email it to me. This requires you to have Blue Waters access, a username. I'll go make sure that your username and the name that's on that are consistent. I'll basically keep this on my laptop for the time being, and then go give you access control to the archive that is hosted on our Lustre file system. So it's there, ready for you, give you read access to it. It's there, ready for you to go. If this is popular and people like it and people start using it, right now the data set we have there is ImageNet as it was in 2011. Since then, they've updated it. There's new releases. One project I hope us and the team will work on is adding more to it. If people are super excited about it, we'll keep it up. If they're not, it'll probably get stale. Well, it'll be what it is. So, right, my email address is there. After I receive your team's access, I will give you. Cool. Okay. All right. So, what is this thing? All right. I mentioned RESTful API and all of that. I have not personally gone through. Any of that process. If you navigate through the ImageNet website, where's my cursor? If you navigate through the ImageNet website, you'll find links to do bulk downloads. Those are somewhere around 1.2 terabytes. You can do a wget on it and try and grab it yourself. I don't know if your storage, your quota for your storage allocation will let you host it once it's expanded. The team has done a little bit of work to try and keep that size under control. So I recommend that you just come down here. All right, so where am I? I'm in my home directory. So what does this mean? The run scripts, I'm going to go through. What time have we got? Okay, the run scripts. I'm going to go through later. Has this path hard-coded in it? I'm basically doing this so that you guys have something tangible in your head when someone says, oh, I got access to ImageNet on Blue Waters. They're tarballs. That's all they are. There are a handful of reasons that I chose to do this. If this gets more popular as the resident data scientist, I would love to set up a more robust data store. Tarballs are fine right now. They're serialized archives. Great. The run scripts I can navigate the tarballs relatively efficiently. Several of my colleagues offered me some suggestions to even improve that efficiency. It's as good as anything else. Another reason I haven't dove into the make this archive a little more modern. This is the native way it comes from ImageNet. During the bulk download, I didn't want to get into any of the details about semantic relationships and syn sets and whatnot. With that said, okay, so that's where the archive literally is. When you run the tools, it will deposit this data onto Scratch. For you guys, it'll deposit onto ImageNet regular. I have an ImageNet too because I have benchmarking work I'm doing. It will build the run scripts. Will do a code tour of later. We'll deposit this data into just raw ImageNet data. Training and validation. The archives make no distinction between training and validation. This is, the team is talking about doing a workshop in June. This is a detail I'll dig more into. When I first wrote the abstract for this talk, I was hoping to get to some of those details today. It's just not going to happen. So training annotations. Whole bunch of synsets. Those are directories. And 0, 2, 7, 8. Let's see, 8, 0, 6. How many of these? Okay, I think I'm going to have to copy something over. And 0, 2, 7, 8, 6, 0, 5, 8. Bam! Annotations are XML files. That was the point. This is nothing fancy. Sorry, I'm an Emacs guy. 8, 6, 0, 5. Oh, of course it's 5, 8. 1, 1, 0, 3, 9. So one detail I'll mention, that index. So you have the synset underscore index. I'm really hoping that's a unique index. The native ImageNet database does not expose its key directly. At least I haven't found that it does. Meaning that I'm guessing because these images are potentially transient, meaning they find a link online, they give it to their team, they annotate it, and then a month later it could get nuked. The actual raw database on the ImageNet side, how those tables are being indexed and sorted and organized is completely up to them. Whenever they expose that database to us, they've given it some arbitrary counter. Whenever I compare these counters to the updated bulk downloads, they are consistent. So I'm hoping they stay consistent. That might be a future disaster waiting to happen. All right, this is what they are. They contain the particular syn set and the height. Let's see, the height and width of the image that this thing belongs to, and the actual bounding box in there. All right, so one idiosyncrasy of this data that I wanted to point out, and the reason I'm doing this little tour, darn, where's my cursor? Oops, sorry. There it is. This file is labeled such and such, synset such and such index. There's an image that I'm going to go point out here in a second that's labeled such and such synset index.jpg. Great, not rocket science. The idiosyncrasy is just because they classified that whole image as representative of whatever that thing is, this XML file can have a long list of additional bounding box with different synsets. Okay, so a small point, but what I'm saying is there's a little bit of a special sauce going on here about the underlying image data and its labels. I'm trying to just blindly take ImageNet data from the source and host it here. I'm not terribly interested in, at least not for a public access, I'm not terribly interested in trying to improve that at all. So whatever ImageNet is doing, that's what I'm trying to do. If they change it, so help us. So annotations are just XML files. Oops, oh, darn it. Where was I? I was in Home, Scratch, ImageNet, to raw ImageNet. Okay, so there's training and validation. Bam. I might have gotten vacuumed. I know I built the validation just the other day. So another detail about Scratch for those validation. Where am I? Okay, I might have gotten vacuumed in these two. This is on the Scratch file system, which means that there's only a month. There's a month time bomb on everything. That's a good and a bad thing. That's a good thing because I don't mind giving every user under the sun these scripts that are going to extract terabytes worth of data and let them go do whatever they want to do with it, because I know it's going to get nuked. That's a bad thing because if you need larger amounts of storage, you either have to ask for a quota increase on your home or get a project that has larger, or you need to use Scratch. So if you're, say, saving your models to Scratch and you train it and it gets unique, that's a problem. Work with the Blue Waters team to sort that detail out. Okay, so what should have happened is when I CD to images, did an LS. Oh, I wonder if Lester was just being slow. At any rate, JPEG images are the synset underscore index.jpg, and they are consistent. That name is consistent with the corresponding XML. The data inside the XML annotation, though, is not necessarily consistent with the synset that the file is labeled. Punchline. Great. Where do we want to go next? Oh, okay. I think I need to go back 2 directories. One more. Darn. TF records. Okay, so that's the raw data. So if you guys, so one thing coming in the pipeline, me and and many members of the team, our Python expert in particular, TensorFlow is great and all, but PyTorch and Cafe2 are, becoming the flavor of the month. They have advantages. There's some things going, interesting features going on with them. PyTorch, my teammate tells me, has native MPI support. TensorFlow does not. And I'm going to admit an embarrassing fact in a little bit that's giving us some trouble. Now, that's not saying that TensorFlow will never have native MPI support. They claim to. We're having a hard time getting it running on Blue Waters. At any rate, usually your pipeline will go, okay, I want these images out of the archive for one reason or another. Now I need to compile them into a data format that indeed TensorFlow likes to use. Reviewing a little bit from earlier in the talk, TensorFlow likes you to spell out a recipe for your operations and then give it over to its mediator to go decide where to put the data and which operations to do. These TF records are a little bit of the beginning of that process. So the second tool that we're going to review in a little bit is compiling those raw images into TF records. So those thousands, I think there was something like 300,000 images in the training set, which is a small amount. I need to make it bigger for these examples. It has gone and combined them into, I went and set the run script to combine groups of images with their annotations into TensorFlow objects called TF records into 1024 different shards. So this is an opportunity for parallelization and optimization of our training. We can pick up a shard, read it in, let TensorFlow optimize the graph on that little shard, and then combine the gradients of the graph later. I ran validation just the other day. Yeah, no, this was all there. I don't know why I guess it just got nuked. Cool. Off. Oh no, that's right. Good. So we have ImageNet. We have the syn sets from WordNet as their annotations and the corresponding bounding boxes and labels and whatnot. And when you get access to this on Blue Waters, it sits in this this directory deep down in the file system of Blue Waters. The run scripts will hopefully take care of all of that for you, and it will populate your user's Scratch directory with raw data and TF records. At which point you can start to train models with. Cool. All right. Blue Waters TensorFlow process. Right now, this is under my personal Git repo. Hopefully, it's blatantly labeled that this is indeed NCSA's work. Already, I have colleagues, Max, who's sitting here with us, going through and code reviewing and making adjustments to this. The future of this is that this is sort of my little sandbox to do research with, to try and get this stuff running and discover best practices. Being a mathematician, I hope to play around with things like transfer learning and plenty of other ideas that my brain is fried at the moment, so I'm not going to go into. So this particular repo is where I try and put all my work that I want to share with the users. This might evolve into a training repo in the near future, to do a little bit of a slimmed down version of it. Period. There are features of this that I'll point out that if you're just some student wanting to get something working, this is a good place to start for now, but there's some baggage that comes with it. Okay, so the process is go clone it. I'm a big GitHub fan. I'm a big version control fan. GitHub, pip, package managers, all that kind of thing. Great. Wherever you clone it, cd into NCSA, Blue Waters, TensorFlow, datasets ImageNet. And when we do the code tour, I'll point these things out. QSub, extract data from archive. This is a parallel job. I think I set it at 64 workers. And it'll go to that tarball sitting in the base of Blue Waters and spit out all the raw images and annotations. Wait for it to be done. The second tool I'm giving you guys, build ImageNet data. This is the thing that looks at the raw data and builds all the TF records. Wait for completion. CD, then go to run scripts in QSub, distributed TensorFlow PBS. This is the top of my stack to run distributed TensorFlow. A lot of the features I've been adding the past few weeks, few days, I have not committed those yet. So we're going to do some code review on my local repo. So what's more, when we go through this example here, oh, the timing's working out okay. Hope everyone's awake. So I pointed out that the output of extract was all those raw images. The output of build ImageNet data was all of those TF records. The output of distributed TensorFlow is this checkpoint directory. Just like I showed you earlier when doing some of the basics on TensorFlow, I created some variables, I did a sum on them, I did a writer, it wrote it, and I popped it up in TensorBoard, and I was able to see the values and the relationships. That is the output of training a model. So, and that will get deposited in this checkpoint directory. We'll go through an example of that. Cool. Let me click on this. Data sets. So this process starts with data sets. ImageNet. You guys might know about Flower and CipherNet, and I'm forgetting what the handwriting image set is. There's that out there. Yes, thank you, NIST. Plenty of others. One project I have with some of my colleagues is discovering more of these data sets. So I'll get on my soapbox and digress for a second here. A lot of this people do on their laptops, to be honest. Whenever I talk to people, doing medical research or whatnot, they're getting relatively small data sets, and they're using R, and they're doing regressions. They're doing fancy regressions. Data science is nothing more than Python on a Mac. Unless you're a statistician, that it's R on whatever you're hosting it on. Part of that reason is it's hard to find large annotated data sets. The image recognition problem is the only one I've found so far, and if members of the audience want to point more out to me, I would be ecstatic. There are hints that there's others out there. But one of the hard things is finding a mature, high-quality data set to start doing something with. When you get these models that have huge amounts of weights and unknowns in them, you need huge amounts of data. So to justify a system like Blue Waters to do data processing, the team is looking for data sets that are ridiculously large, and to do something meaningful with them need these super deep neural networks, or whatever model is the flavor of the month. So there we go. The team is looking for additional problems besides just this feature detection one that would be interesting to do on Blue Waters. We know our users are doing some machine learning, some model building, but we're not necessarily convinced that they're doing the true distributed type things that is what we'd like to do. Okay, soapbox done. ImageNet. Okay, so what did I say the process flow? The first one was extract data from archive. For those of you who have done work on Blue Waters, this is a pretty vanilla PBS script. Because I come from, well, okay. I think Donald Knuth had a quote, something about, the fewer lines of code you have, the better your program is. I think that's right. So this one is a little bit longer. I'm trying to keep these as small and self-contained as possible. Some things you can play with on this, though. What did I do? Processors per node. So if you remember earlier, I went through, let me make this bigger. I went to great lengths to distinguish the different features of Blue Waters, the fact that we have two different kinds of nodes, XE nodes and XK nodes. XE nodes have only CPUs, XK nodes have GPUs. The extraction process, there's no image processing here. There's no actual TensorFlow things. It's just fancy shell scripting and tarballs. Play around with your concurrency to your heart's content. Logs. I'm relatively new to the HPC community. I decided I like spitting out my logs in a more self-contained area and labeling them something a little more meaningful. My personal scripts, I like getting emails when things finish, especially if I'm walking out for the day and I'm at home and it's 7 o'clock and I get an email that says, it was successful. I like seeing that. So you can play around with that as much as you want. These scripts require you to launch them from this directory. As I learn more about best practices and the way scientists like to work on Blue Waters, we can change this around and improve on that. Cool. This, you should, hopefully you'll never have to change. Or the Blue Waters team will change this as we decide to host this data in different ways. This is something for you to change. One thing that I promised in the abstract that we're not going to get to today is the validation portion of all this. I'll talk more about that later. But this script will simultaneously do, or will synchronously do your training set, and then kick it off for your and then once it's done, kick it off for your validation set. Okay. Why did I comment those out? Oh, that's why. This thing. This is a piece of special sauce that during a workshop I'll explain more. So down here I have all these commented out. Oh yeah, training's fine. Ooh, maybe it should be train. I am providing you my pre-cooked set of training images and my pre-cooked set of validation images. These aren't particularly special. They won't necessarily train a model better than anything else. They're my attempt to give you something to start playing with right out of the box. If you want to do your own work, you will generate these yourself. If you want bigger image sets, maybe you want to take everything from your Facebook and throw it in here. You will then have to go figure out how to do that and pull it down to Blue Waters and add that to this file. So let's go back just a second. So what are these things? They're nothing fancy. Hope this doesn't crash. I might have to hop over too. They are nothing more than the synset and the file name. The reason you have to keep this consistent is because of that problem I mentioned from the XMLs. You might be interested in training an image with a synset that is an annotation inside of something else. So for instance, one of the first bugs I ran into, the synset was for bus stop, but the particular feature it was trying to train was stop sign. Okay, fine. The XML file was stored under the bus stop synset. So this is basically a mapping for all those weird cases. Furthermore, it gives you more data to play with. A lot of these images have multiple things you can train them with. Okay. So yeah, if you want to pull down everything from your, I don't know, Instagram or Twitter feed and start putting it in here, this is for you to muck with. All right, I don't want to belabor this too much more. Home scratch, this is as good a directory to stick it as any. If you have your own custom allocations and want to muck with it, by all means. So just cleaning, trying to figure out load Python. So this is all pretty standard. Create synset list. I don't know if my colleagues like me doing things like this, doing inlines, Pythons. I really like the three big basic Python data structures: lists, sets, and dictionaries. Extract ImageNet. Okay, great. I think that was all the details you should know about. So when you get this, you can toggle between training and validation and this specific list of things you want to extract. I give you my cooked up version of it. There's nothing special about it. In fact, there very easily could be problems with it. But it's at least something to help you get started, and you can modify that however you want. The second step was build ImageNet data. Same kind of theme. You can toggle between training and validation. Shards. Your training set will typically be larger than your validation set. That's not a hard rule. So to get a better balance of file size, your training set, you'll usually want to split that into more TF record files than your validation set. So the common practice is to do 1024 for training and then 128 for validation. There are some details in there about your devices. You want those. Oh crap. Your devices, you want those to be, you want your shards to be divisible by the number of devices, kind of thing. So there are some limitations. Cool. Okay, so the thing I need to commit to the repo probably after this session is the thing under run scripts. So distributed TensorFlow launch. I've done a lot of work on this, updating it to modern practices that I'm about to commit. So let's go. This, as it stands right now, this thing out of the box basically runs the Google supplied benchmark scripts. Those are fine if you want to use those as examples. My experience with them is they are indeed running the model, but when they're saving the tensor board, it's screwing up. Race conditions, something I have no idea why. So I haven't been able to use the benchmarks to actually do validation with. That's why I'm sort of I'm in the process of abandoning the benchmarks and providing you guys with something a little nicer. This just, where's my cursor? There it is. Okay, so let's go look at this distributed TensorFlow. Come on, oops. Where am I? Home/development, BW. BWPY, NCSA, this guy, run scripts, Emacs, distributed TensorFlow, bam. All right, a lot of the same kind of things we were seeing earlier. Okay, this is one detail that I forgot to mention earlier. When you're using GPUs on distributed TensorFlow, there are other ways of achieving this same effect. Processors per node is 1. So 1 node, 1 processor per node, and that will make sure that TensorFlow only tries to grab 1 GPU. My experience was that whenever I tried to grab more, there are multiple TensorFlow instances trying to grab the same piece of hardware, and they're not cooperating well. Like I was telling you earlier, TensorFlow natively is natively written in C++. So all its multi-threading, all of its CUDA kind of work happens way underneath the Python layer. So it's taking full advantage of the underlying base hardware. So this just keeps multiple TensorFlow instances from running on a single XK node and gumming it up. Number of steps. This is how many. This is basically how many images does it push through. In parallel, you multiply that by the number of workers you have. Train directory. Oh, I did. Okay. So this is where the output will get stored. I changed it a little bit because I didn't want 25,000 of them. That's it. Most for at least in terms of the run script. So things you have to play with: the train directory or the data directory. So this points to Scratch, ImageNet2, TF records. And if you're running a training if you're running a training graph, you point it to your training TF records, and you tell how many steps you want to go through. Number of training samples. This is how many lines you have in that in the training files.txt. If it's wrong, it will mismatch images to tensor operations, and you'll get lots of ugly errors. Batch size, this is how many images it tries to load all at once and perform one gradient descent with. So for those of you who know, it's doing a mixture of gradient descent and stochastic gradient descent. Load in a batch of 32, compute your gradients, advance, load in the next set of a batch of 32, compute your gradients. I have successfully wrapped most of the nitty-gritty details inside of run command. Where is it? Oh, here it is. This Python thing I'm calling main. It's under BW distributed train. Main. Most of the distributed work and the distributed TensorFlow example is in here. 6 minutes. Think I can do it? I didn't count for slow brain and getting tired. All right. So this is where all the example magic is happening. This is as the team develops best practices. This is the thing that I'll update. I might change it from main to train and then a separate validation. One thing I found about surfing all the TensorFlow GitHubs these kinds of things, they pack a lot of features into one top-level command. I actually don't like that. That's not the way I like developing code. So I'm building these out so that you have fewer arguments you can pass to the basically the to just the training session. Fewer arguments you can pass to just the validation session and whatnot. Okay. This is TensorFlow. This is a top-level thing. This is the thing that gets run. TensorFlow app.main. This thing looks inside of your file and looks for a function called main. You can pass it, you can overload. Again, this is a mediator pattern. So app is the mediator, run is the thing that looks at its environment. You can pass custom things here. Go look at the docs to decide how to do that. I haven't thought of a good reason to do anything but main. If I remember correctly, I think this passes console arguments. TensorFlow has its own argparse system. You can use this or TensorFlows. Get hostname. This is the part that that's figuring out when AP run runs this 25 bazillion times or however big you want your job. This is the part that goes and identifies which unique worker am I. Unfortunately, the detail we were not able to get to today is talking about how TensorFlow out of the box does parallelization, or how it does its cluster management. It has things called parameter servers, parameter workers, servers, and workers. So I want to point this out, and I want to show you all the new fancy features going on in here. We're hoping to blow that away very soon. Cray has been doing their own development to support these machine learning packages. They provided a plugin that uses the Gemini native NICs and MPI to be passing around gradients between all the workers at close to hardware level. Its performance, the benchmarking I've done on it so far, its performance is spectacular. I basically provided this example so that it's consistent with the tutorials you would find on tensorflow.com. In the near future, we expect to blow away the parameter server portion of this and simply keep the worker portion of it and let the Cray plugin manage all the gradients going back and forth. So with that said, in 2 minutes, it's like the professor trying to give you one last example. Some of the special sauce I give you here is identifying all the indices and whatnot, figuring it all out. This variable here, TF PS host ports, TF worker host ports. TensorFlow, when doing its distributed TensorFlow, wants a description of the cluster. That is a list. It wants a list of host names and ports to broadcast and listen on. And it wants to know which ones of those you want to use for a parameter server and which ones it wants to know to use it as a worker. If Google had it their way, that's all you would have to do. All the practical applications I've seen of this, there's some extra hoops you got to jump through. So that's the special sauce. Getting, for Blue Waters, getting the host names for NIDs, the host names, constructing a cluster spec, starting a server, as a cluster. This is the description of the whole thing. And this guy here is your local instance. You're telling it, I am the whatever index of the parameter server or worker. Up in the train, This is where we do all the build a graph for the local worker. Well, it should be shared. That's magic that TensorFlow is doing for us with its mediator pattern. Specifying the specific devices, bouncing between CPUs and GPUs. So here's your example of the naming schemas to reference all the different pieces. Oh, device GPU, contrib framework, and this guy here. Second to last piece of secret sauce. This is the thing that is supposed to be managing where all the variables are getting passed around the cluster. So whether it's hosted locally, remotely, whether it's replicated, or just a ghost of the variable on the local, and how to pass it all around. And then the session that actually runs, batch norm, monitor training session. So from the example at the very beginning, with sesh as session, monitor session, this is it, and it runs all the training ops. So all the code above is a little bit of recycled code from Google's models repo, and then some of our stuff I had to do to try and jimmy this thing to work. Whew. Questions?
Okay, if you have any questions, feel free to post them to the YouTube live chat. While we're waiting to see if there are any questions, you mentioned a workshop, or you want to say anything about that? What's happening, when that might happen?
So the exact date, I don't simply don't remember. June is our target. There's a handful of other deadlines for the engineers around here, and June is right after that. Basically, the goal is to do everything we talked about here, but do it with a smaller training set. Instead of trying to train an entire huge inception model with 1,000, by the way, this is being done on 1,000 different labels, for better or worse. You can do more or less, go work out your run scripts to do that. So for the workshop, we want to parse all this down and maybe just do, does this picture have a kitten in it or not? Something a little cuter like that. If you go to some of these TensorFlow workshops, those are the kinds of problems they do, is they build up these smaller models that will detect only a couple of features. Furthermore, they get these models to be around 80% accuracy, where right now the model that where state of the art is getting 90% some accuracy. So yeah, workshop will be going through this. Maybe less theory, maybe more definitely a lot more hands-on, actually doing what I was describing.
And for our viewers, that'll be webcast. If you're interested in learning more about it or being on a mailing list, you can email bw-eot@ncsa.illinois.edu, and we'll be sure to let you know when that is and how to register. No questions? I don't see any other questions here, so join me in thanking Aaron Saxton for a great presentation today. Thank you very much, Aaron.
Thank you.
Just want to alert you to next upcoming webinars next week, next Wednesday, February 14th. Dan Katz will be talking about sustaining research software. And then February 28th, Matt Turk will be talking about analysis and visualization with the YT. We always look forward to your comments and suggestions for other topics that we should try to schedule that would be of interest to you. With that, we thank you for joining, and we look forward to seeing you at a future webinar.